All right, so I checked some of the questions on Campusware. As you see, can you post chapter 6 of the textbook, which is already posted, or the handouts that you need for your for the to solve the homework number 6 is here. Week number 5, chapter 6. If you open that one, it shows these are the steps, So all you need is wastewater treatments. That's section 5 of that chapter. So if you scroll down all the way, all right, so this is wastewater treatments. This is the sections that covers the wastewater treatment section of what we cover. So it's a primary treatments, secondary treatments. So these are the, you can see the equations that you need for your solving the problems are here. Equation 47, 48. So these are all part of the slide too. So everything that is here is also in the slide. So these are the different stuff. These are the rate equations. And you can see there are some problems that you can use to understand that, that problem, solving those problems. And these are the example problems in the textbook, which will help you solve the question number 1 and 2. So this is already some example here. And then after that, suspended growth treatment, all that was in the lecture 2, the lecture second half of, no, actually it's not true. No, this is something I already also explained in the lecture 1. So the only thing that, let me see. These equations are already in that lecture. So I'm just checking what is not there. Okay, so these attached growth treatments, these are the things they are not part of the homework questions. These are conceptual understanding, which I recorded and posted just now. I just recorded it because I didn't record before, which I'll post it after this class. So those will for your understanding. It's not really you need for a homework. But what I did is I added some extra examples based on say, homework question number 3 and 4. So if you go back to the, let's see, if you go back to the this week, and if you see, oh, I see. I think the confusion might be because there is also written chapter 6 here, waste management, because that chapter has all the different sections. Okay, so it's not necessarily that this chapter has, this is the chapter. As you see, this is only section 7 of chapter 6. So don't open this one if you want to look for wastewater related questions. But anyway, let's open the homework question because I got some questions related to this. So question 1, biological treatment. Those are the examples 14. If you go to the example in the textbook, you should be able to solve all these because these are just one line answer. You look for the question. For instance, what is the waste activated sludge flow rate? So that's the amount of waste leave the biological treatment unit. So you can see the equations, and then wherever that flow rate is, you just plug the value or do the mass balance and then get the answer. So I'll have some one example extra so that you if you have difficulties. And also I recognize that there is less TSS on this time. So that means I'll give you more examples. So I'll try to replace that TSS by adding more example to what I provide. So I'll add more examples to what I recorded today and I'll post it so that you have some more understanding. But this is basically the equations already there. And the question number 3 and 4, these are, as you see, these equations are given everything. So this is just a wastewater treatment plants, the primary, secondary. The only difference here is that the amount of the effluents is now getting into the river. Okay, and the river DO is going to change because of that. That's something you already learned in the previous homework. So you're going to apply the same concept what you learned before in the homework number 5 or 4, I don't remember, just to solve it. So it's the same question. This is just a mass balance question. This is not even part of the wastewater You don't have to add some other equations, what you already have there. So what I'll do is um, I will add some more example question like question number 3 and 4 in my discussions or in my recording for the second half of a wastewater so that you at least see how I solve those. So it will give an idea how to use mass balance to solve any kind of this problem. So if you have difficulty on homework number 6, keep sending email, not email, campusware, wherever you have difficulty. That will help me see what kind of example I should post. Okay, so only when you write about it, then only I know. Otherwise, I assume that you already know how to do this homework. Again, these are mass balance questions. These are not really any new different question. For instance, if you see what is the primary treatment unit, the primary treatment unit has area this. What is the settling velocity? Well, settling velocity, you already know how to calculate. Okay, so you need size, you need all that factor. So those are you can find those out. But I'll give more examples. And again, this is not due until Tuesday. So you will have some more discussion session on Monday and Wednesday, Monday and Tuesday, so that you have more chance in case you have difficulty this week. Okay, so that's all about the questions. Let me see if there is any other questions. Um, Question 1, is the millimeter refer to the maximum microbial growth? So I'll check those specific question and I'll post it. So again, can you post chapter 6? It's already posted on week number 5. Okay, if you don't have that one, let me know. Okay, so I answer most other. I will check other later. Okay, so that's all about the questions. Again, right now we have 63 students, which is great to see because I a lot of times when we have in-person class, people really complain about having a class on the day before Thanksgiving. They all want to travel. This is new. This I'm excited because I feel like this is normal now. So let me share the screen. Uh, and thank you all for joining the class today. I know a lot of things go into mind, but anytime I see people, it makes me feel normal. Otherwise, I'm not seeing anybody. I'm just staying at home and watching from my window outside students walking. Right. Let's see. Where is the screen? The screen share. Share the screen. Okay, we have quite a bit to cover, but it's really like simple stuff. It's really not very highly. Um, Few examples. Um, okay. All right. So we are 15 minutes up into the class, and we today we are going to discuss about wastewater treatment technology. Not wastewater, waste treatment technology. It could be solid waste. It could be contaminated groundwater. It could be any water that is polluted. Nothing to do with municipal wastewater. Okay. So these are hazardous waste. This could be hazardous or non-hazardous waste. So let me minimize the screen. Okay. Just one announcement. Homework 6 is due on Tuesday next week. We'll have some discussion session on Monday. I will also request the TAs to have multiple discussion session on Monday and Tuesday if you guys need it. That way you have all the help you need to solve homework number 6. Again, wastewater treatment lectures too. I'll post more example. I already record for the basic part of it, and with some examples. But I also see on campus where there are some more questions, so I will post more example based on those questions. Again, if you have difficulties, please post any questions on campusware. That way I know what I need to have more examples on it. Or what I'll do is I'll give the example questions to TA so that on Monday and Tuesday they will able to explain those. Either way, just keep asking, anything you guys need help with. Office hour, no office hour this week because of Thanksgiving. And again, this reading of this chapter is chapter 6, section. This is not section 5. This is, I think, section 7, if I correct. The pages are corrected, and some of the materials we cover here is also part of the open access link, websites that's provided. And mostly this what we are going to cover this class is this particular class will be mostly short questions. There are no long questions for the final exam. So when you learn about different topics here, think of concept more than the trying to understand the bigger questions, or the quantitative questions. There are some quantitative questions, but those are very easy to solve. Just plug in the value and get the answers. So what you're going to learn today is different types of way to treat groundwater. Again, this is extension of CE164. So these are the things you learn a lot details in CE164. So I'm just giving you a flavor of that course, um, what we are going to learn there. So first, what we are going to learn is different types of treatment technology to treat all the groundwater. So there are ex situ, in situ. In situ means right inside the groundwater without really taking it out. Ex situ means you pump the groundwater outside and then you degrade them or remove the pollutants. And also we'll talk about how to deal with non-hazardous waste like municipal waste, that activated straws or anything like plastic, all the stuffs that you dump in your trash can. So where they go, how they are going to be used. And we'll give you a little bit flavor about how to the concept of recovering some resource out of those waste, which will be actually the last week of the class, but I'll give you some flavor of how you can extract some energy from this waste. Um, so first thing is ex situ remediations. Ex situ again means remediation of, we are talking about groundwater. So when you want to treat groundwater, because that's something is used for drinking water, so that's why it has higher priority. So when you treat it, it what it does, you have to pump most of the time, and you treat externally and then pump it back so that you have the similar flow in groundwater. So these are different ex situ. Again, ex situ means outside. So that means you remove the groundwater from aquifer, and you do all this thing. And there are also ex situ treatment technology for related to contaminated soil, because that soil is what release the pollutant to groundwater. So these are the mixed different things. So this is for the soil above the groundwater level, so which is the source of pollutant. So you can just dig and dump all the contaminate soil into landfills so that there is no continuous pollution of groundwater. Then these are all the other things that I explained here related to treatments of contaminated water. So you pump it, and then you either have advanced oxidations where you add some kind of oxidants, remove it, or it could be air stripping, so that no, because if you are removing any time volatile compounds, something that can easily become gaseous state, you just bubble air through it so that it allow the methane gas or all this gas to escape, and then you capture them, and either you burn it, or you capture and for use. And then we have carbon adsorption, which we are going to discuss today a little bit more extensively, where you use activated carbon to remove any kind of organic pollutants. It removes some inorganic, but not that much. Then also the most popular method is membrane treatments. Membrane is basically, it's a membrane. It's a small size, nanometer size pore. So you pump water through it, so the ion cannot even move. So that means you have just water molecules. Very few ions can move. Reverse osmosis membrane I'm talking about. So there are all the different techniques. Then ion exchange that remove any kind of ionic pollutants, or neutral species won't work. Then there are also bioremediations where you, similar to wastewater treatments, you pump the water. If you have lots of organic, you grow bacteria in it, or the microorganism that can degrade those pollutants, and then you inject it back. Typical is very slow, so that's why ex-situ treatments of bioremediation is not feasible in many cases. Then finally is the thermal incinerations, where you actually dump any kind of waste you produce during these treatments by burning them. So these are different process. What you got to remember is when this each system would be more efficient. So think of advanced oxidations. Anytime I ask whether this is efficient or not, as you see this advanced oxidation means the pollutant has to be oxidized. So if you have a compound that cannot be oxidized, you can't be using this method. So you have to think of any what you are using. Is this it can be oxidized or not? If it can, then this method would work. Air stripping. The whole concept of air stripping is the fact that you can evaporate or make the gas escape. So that will only work if the compound that you are interested is volatile. If it is not volatile, you can't use this method. For instance, if I ask, can you remove air PFAS using air stripping? Based on the structure, PFAS is not volatile. That means it will stay in water or stay in solid more than going into air. So that means you can't use this method for that method. But if I ask, can you remove methane by air stripping? It's yes, because methane is highly volatile. Same thing. If I ask you when carbon adsorption is efficient, well, you have to look for if the contaminant is hydrophobic. Means if it has lots of carbon, then it will stick with carbon. Membrane treatments can remove everything. There is no selection here. Everything can be removed, even small ions. So that's why membrane is used for desalinations, where you can even remove sodium, so Na plus. Ion exchange, again, it can remove ionic pollutants. So that means if I say, can you remove PFAS, which is non-ionic, then obviously it can work. So you got to think of all that, but just know when it works, when it doesn't work. So what we are going to discuss today is carbon adsorption techniques. The technique is very similar to what you learned before for any adsorption of pollutants in soil. This is the same concept. The difference is you use activated carbon. Why it's called activated carbon? Well, think of how activated carbon is being produced. We'll discuss a little bit more, but just know that you take this activated carbon, put inside this blue tank that you see over here, just fill them with a tank. So that means you have to think of the size, because the more that will determine how much activated carbon you can pack inside. It also determines the porosity. It's the same concept as retardation factor. More porosity, faster it's going to move through it, but it's not going to interact with the activated carbon. So you have to make the size smaller. So again, these are a couple of things they have to determine. Empty bed contact time means how long it takes for the water to move through the through the activated carbon tank through that pores. Usually it should be 5 to 20 minutes, because you want to treat a lot of water. And the activated carbon surface area has to be very high, because the adsorption depends on the sticking on the surface. So the more the surface, more the removal. So that means if you make the particle size smaller, it has more surface area. But you have to also remember activated carbons, the reason it's called activated is because it has lots of pores, and those pores are cleaned. So if you have a big chunk of activated carbon, it's not the surface here. It has many pores inside. So they stick inside those micro or nanopores. So you have to think of all that. Then again, it depends on the contaminant type, mostly number of carbon, because as I said, the adsorption is based on the carbon. So the more number of carbon in the contaminants, it will more attraction towards the carbon materials. So just look for how many carbons is there, what's the solubility, all that stuff. Also, it depends on the water chemistry, because any adsorption, it depends on the pH as well as the interaction of that contaminants with the surface. So you got to look for those constituents of water that could affect that adsorption techniques. So these are the design calculations that you learn in CE164. But here, what you are going to learn is how much carbon you need for a treatment goal. That's the only problems I'll solve. So these are the things we are not going to learn in this class. This is just the design calculation you need to learn if you are taking CE164. So as I said, I asked this question: why activated carbon is such an excellent adsorbent? So first of all, always you hear this is activated. What does that even mean? Carbon, you all understand. If you take a charcoal, that's carbon. If you take wood, that is also carbon. So what's the difference here? Well, first think of how activated carbon is being produced. So it is produced by, so you take a wood piece. Let's say I'm just going to draw a wood piece. Okay, so this is a wood piece in my view, and you want to make it activate carbon. If you think of wood, normal woods, they always porous because they transport all the water nutrients for the trees. So it has really micro or nano pores. That's how they use capillary action to draw water inside them. So now if you burn them, if you just burn them like normal wood and during campfire, you will see that what remaining is ash. There is nothing else remaining. That's because you burn all the carbon to carbon dioxide. So if you burn any woods with oxygen, it become carbon dioxide, and all inorganic become ash. Okay. Um, but what if you burn this carbon? Means you heat it up. So this is heat. Okay. If you do that one, and then let's say I'm going to add nitrogen, because you have to have some space, so that space you fill with nitrogen instead of oxygen, and you just heat it then. So now this oxygen is not there to become carbon dioxide. So what you'll have is, because of heat, the bonds are going to start breaking up. Okay, so you'll get some kind of reaction. There will be always some impurity of oxygen already present as chemical bond. So those oxygen will release. So what will have remaining is just carbon with some functional group, like you see over here, this carbon, and and sometimes you get biogas and some ash. Okay, so this is what we call burned carbon. Okay, burned carbon but without oxygen. So that means you retain those structure. That structure has this kind of graphite like structure or fused structure with some functional group. And now what you do is they do not have high surface area, because when you burn, they are stuck inside the pores and all that. So now what you do is you apply steam on it, high temperature steam, so that you can open up that pores. So if you apply this, take this carbon. So I'm just going to take carbon and steam. It is called activated carbon. There are multiple ways. It's not just steam. There are chemical method. You can add this in sodium high in acidic solution or basic solution to dissolve anything inside those pore, all the ash and all that stuff, so that become activated. What it means? The activated means it clear up the pores, clear the pores, so that those are now accessible for adsorption. So that's how activated carbon is being produced. Again, this is a very excellent adsorbent. It's produced from raw material like woods, and that's why it can be it is more sustainable, in the sense that you get from natural materials, not from chemicals. The another advantage is that activated carbon, when you fuse them like this, bacteria cannot decompose those bonds. So that means this activated carbon will stay there for like 100 years. So that means you are not expected for this activated carbon to become carbon dioxide at some point. So, so these are the things that is being used. And now question is, how they remove it. All the hydrophobic organic contaminants, so organic chemicals mostly will adsorb here, okay, on this carbon-carbon bond by hydrophobic interactions. Any kind of metal, let's say copper, 2 plus, think of zinc, 2 plus, let's say lead, you have also copper 1 plus. All these positively charged, they are going to stick around with this negative charge, like the functional group, okay, the O. So this oxygen functional group will bind with this negative positively charged metals. So that's why activated carbon can remove different types of pollutants. The only limitations is that these are like any adsorption techniques, it depends on the surface properties. So once those surfaces are gone, you cannot continue absorb more pollutants. So that's why you have this activated carbon will be exhausted at some point. You got to regenerate it by heating it up again, like the same way you do pyrolysis, so that you can burn all the surface chemicals, and then you can reuse again. And so that's one of the things. And then once you start, every time you regenerate that activated carbon, there are some absorption capacity will be lost forever. After a point, it's not economical. You have to dump it up. And again, these are adsorption. So it remove pollutant from one phase, which is water here, to activate carbon. So now, even though your water is treated or clean, now you're creating this polluted activated carbon. So you have to dump them somewhere in landfill. So that's the only other limitations. It's not a destructive techniques. So now that you understand the process, everything, let's solve the problem. You already know the adsorption, what does that mean, all that stuff. So let's see how to solve this. This was a part of the last uh, lecture question. I want to solve it here. Removal of contaminant by activated carbon is expressed by friendly isotherm in the form of Q equal to zero point 0.1 C to the power 0.3. So here Q is concentration of pollutants in activated carbon, or the adsorbed pollutants. So that's why mole of pollutants per gram of activated carbon. Okay. So this is mole per gram of activated carbon. And is related to C, the concentration of pollutants remain in the water after adsorption. So this C is the concentration at the equilibrium. So that means it's everything after it's being removed. So this is concentration mole per liter, that's of water. How much activated carbon should be added to treat aqueous solution concentration of 0.45 moles per liter to reduce its concentration to achieve a treatment goal of 99%. So what you are saying is your contact. So let's say this is activated carbon, okay, and you are injecting a pollutant. It has the pollutant concentration, which is C in, is 0.45 moles per liter, okay, and you want to treat it such a way that your C out 99% is removed. That means 0.01% remaining of C in. Okay. Or another way to say is if I if I want to write it properly, so this will be 1 minus 99%, also 0.99 times C in, that 99% removal. So only 1% remain. So that will be 0.01 C in, and that will be 0.01 times 0.45 moles per liter, which will be well 0.0045 moles per liter. Okay, so that's the effluent. And you have to treat, the volume of water that you have to treat is 1000 gallons per day. So that's the first thing, how much activated carbon you need to treat. So first of all, let's think of what that means now. So you have something coming in, something living, that means you know amount of activated carbon, amount of pollutants removed per liter of treatments, because you know C in, C out, you know the volume, you know the amount of pollutant removed. Now you know what's the capacity of activated carbon for a concentration here. What would be the capacity of activated carbon? So what is the concentration here? The C is the concentration of pollutants in the effluents after the removal. So that C is here, whatever the C, this C out. Okay, so this will be C out. So that's after the adsorption. This is not before. So if you know C out, you know how much pollutants goes to activated carbon per for a desired concentration in water. If you know this one, that means you know how much pollutants can be removed per gram of activated carbon, and you know how much pollutants are totally removed. So let's try this one. So solution again, first thing you have to do is how much pollutants are removed. So contaminant removed. So pollutant removed. That's what you have to first calculate. So that will be in terms of moles. Okay, so we want to know moles of pollutant. So again, mass balance, what's the amount removed is whatever coming in, mass coming in minus mass out. M in minus M out. So M in is C concentration in times volume minus C out times volume. Okay, so let's write this one. So that would be, this is a volume times C in minus C out, and C out is 0.01% of C in. So 0.01% of C in is C out based on 99% removal. So that means you are looking for here is 0.99 times volumes times C in. If you So that's the 99% remove. So whatever coming in, so if you see, this is the amount of things coming in, V volume times C in. So let's write this one, 0.99% removal times volume. Volume is 1,000 gallon per day. And you got to make 1 gallon to a liter, so 3.785 liters. And then you have to do concentration in, which is 0.45 moles per liter. So liter cancel, gallon cancel, then you'll get moles per day, amount of pollutant removed per day. Okay, so whatever that units, so you just write moles per day. Again, in exam, if you just do this way, you get full points. You don't have to really use the calculators to write the whole.
Professor,
Yes.
I have a question.
Yeah.
On this one, why are you multiplying times the rate, like the 1,000 gallons per day
So,
instead of?
okay. So pollutant removed per day. I have to write it
Oh,
here. Okay.
sorry. Oh yeah. Oh, never mind. That's the because Q is the volumetric rate.
Yes. Yes.
Okay.
So
Thank you.
here it's actually Q. This is Q. Okay. So this is 10,000 gallon per day. So this is M, then it become per day, M dot. Okay. All right. So it's really, you know what, I should not do all this messed up because we already explained everything. So let's keep it Q just so that no, this is in per day. Okay. If you don't write day here, it's fine. It just you that all it means is per day is how much is removed. Okay. You don't have to
Okay.
take the day.
Thank you.
All right, so we now know how much pollutants are removed. So let's write this one M pollutant. Okay, because I don't want to calculate for the sake of time. So now you know how much pollutants are removed. So now you know what's the absorption. All you have to do now is what's the absorption capacity of activated carbon for a treatment goal, which is written here, Q. So absorption capacity is small. The answer is the unit is moles of pollutants per gram of activated carbon. Okay, is 0.01 times C to the power 0.3. Okay, so again, this C is the treatment goal. So whatever the your effluent is, it's not before adsorption, it's after adsorption. It's because after equilibrium. So 0.01 times C is C, so whatever C out. So that's a 0.0045 moles per liter times 0. 3. Again, these are already unit balanced because of the constant. That constant has a different unit, such a way that the answer will be moles per gram activated carbon. So you get something, okay? So that whatever that answer, let's say I am going to write it. Um, I mean, let's say adsorption capacity. Activated carbon become adsorption capacity. So AC is the same thing. So let's say capacity, whatever that term, uh, moles per gram of activated carbon. So that means you can remove this much mole of pollutants per 1 gram of activated carbon you use before it is exhausted or you don't want to use it. So now how much activated carbon? So mass of activated carbon needed should be more pollutant load, pollutant removed divided by capacity. So you take this one and then divided by this one. So this is again moles divided by mole per gram of activated carbon. So your answer will be gram of activated carbon. So you can convert that to kilograms or whatever the unit. Okay. The next question is what would be the height of activated carbon tank like this design if the area is 10 meters square? So this is unpacking density or bulk density is 1.3 centimeters gram per centimeter square. So that's basically I'm asking how tall this one would be. It would dump all these activated carbons. You know the mass. You know mass of activated carbon. Okay. And you know the size of this one. So and you know also the bulk density means you know how much volume it will occupy if you add certain amount of activated carbon. So if you know the volume, basically you are going to say is that whatever the volume of this, let's say what is the area. So let's calculate what's the volume of activated carbon. So this is A, B. Volume of activated carbon is whatever this is mass of activated carbon. Okay, mass of activated carbon, and the density is mass per volume, right? So if you divide by density or bulk density, you get the volume of activated carbon. Okay. If you know the volume of activated carbon, if you start pouring in, you just have to calculate how high it will go. If you know the area, so this should be the volume of tank. Volume of tank is a cylinder. So if you know the area, the area is 10 meters square. So this is area times height of that tank. Okay. So H of tank would be volume of activated carbon divided by area. You already calculate volume of activated carbon here. You know the area is given, then you know the tank size. So that's how you determine how big the tank would be. But now you might find that the tank will be like 20 meters. So now is it feasible to have a 20-meter tank? No, because you can't really build something that big. It's not efficient because you have to pump water through it. So what people do normally is they break it down to multiple activated carbon tanks. So that's how you see over here. You have like three tanks. That means the equivalent height will be if you add them together. These are on series. They are not in parallel. The another advantage is that once one activated carbon tank is exhausted, you don't have to stop you don't have to really um, uh, wait the stop the entire treatments. All you have to do is bypass it and remove that and put in another one. That's how they are designed in a series. Any questions? This is the most important treatment system for any drinking water treatment systems. This is normally used for if you go to any groundwater treatments. And you'll learn a lot more about how to design it in CE164. This is just give you just a basic idea of to calculate how much design goals would be. All right.
Is that
So
equation, the Q equals 0.1 C to the power? Is that a standard equation, or is that just kind of something that was given for this particular problem?
This is given for a particular problem. This is experimental determined. So this is experimentally determined. Okay, so this is called adsorption isotherm. So like linear isotherm, this is something people do determine for different types of activated carbon. So this has to be given to you.
Okay.
All right. So now that you learn, activated carbon can remove anything which is a mostly organic pollutant, which can be adsorbed to other.
Sorry,
Yeah.
it should be 0.1 for absorption capacity.
Let's see.
0.1.
Oh, you're
Yeah,
right. I have a typo here. This is
yeah,
0.1. Thank you. So let me 0.1.
yeah.
Thanks. All right. So air stripping. What activated carbon cannot do is you cannot remove anything which doesn't attach to organic activated carbon. So because it rely on activated carbon to be absorbing those pollutants. There are two type of pollutant that may not be easily absorbed. First, if it is a gas, gas doesn't have some gas do absorb if organic volatile compounds, but many other cannot. So gaseous forms are more cheaper to remove by just air stripping because it has just tendencies to get into air. And then another thing is what activated carbon cannot do is anything which is highly dissolved pollutant. If it is dissolved, it doesn't have a tendency to be absorbed on carbon-based materials. So for dissolved pollutant, you have to do something else. For instance, redox or the advanced oxidations, where you add some kind of pollutant, some kind of bleach or oxidant, so it will remove anything which is dissolved. Or you can use RO. But if it is gas or high, the Henry constant is high or it is highly volatile, you can use air stripping. The advantage of air stripping is that it doesn't require any kind of waste material because here you are producing another activated carbon as a waste. Here you don't. You just have to let it escape. But now there is always a challenge. If you let it escape to the air, you are also polluting air, and you don't want to inhale those volatile organic compounds, which are also kind of carcinogen. So that's why you see what people do is they actually capture those gas. Uh, so normally how it works, what you do is you have this kind of bead here. You just put lots of beads with high surface area because you want to let it escape to the air, um, and then you spray water here, and and then you blow air from the bottom. So this is air, okay, and water coming in here. So now if you are blowing water or blowing air, the water will become droplet and small sprinkle. And now they have more surface area. That bubble, the water bubbles, has a lot of this surface area. So that's the key. The smaller and smaller and smaller that become that bubble, the gas will escape from that water because now the air is around it. So it has more tendency to get into the air phase. So ultimately, your clean water is going to come out here. So this is clean water. This is this is polluted water. This is clean air, and then you have also you have a collection system, polluted air. And then you take that polluted air and pass through a activated carbon or any kind of adsorption membrane, adsorption system, which can actually strip that polluted gas. That way you don't pollute the air itself, and then you can deal with that gas. Or if it is methane or some kind, you can always find a way to separate them and reuse it for energy. So this is air stripping method. We don't have to do any calculation here in this class. Just know that this is the things that how it works. Any question? Okay, so this is just a schematic to show that you have aquifer, you have contaminated groundwaters, And there are many different systems you can use to remove pollutant. So as I said, this particular, this is air stripping. If you see, this is you pump the groundwater, put on the top, and then you blow air through it, and that's how you air in, air out. So escape in the atmosphere here, and then you have clean water coming out. So that's air stripping. So this is ex-situ because you are treating water outside the aquifer. And then if you think of the same techniques, you can do in situ by actually adding air in the groundwater. So this techniques, your air sparging. If you see these techniques, all you do is you pump air through it, so that the water has a lot of these bubbles of air, and what it does is that bubbles will attract lots of methane gas inside it, and so that's how you can let the air escape into the subsurface. So that means your all the pollutants will become air phase, and then they will permeate out of the ground. So that means now you are inhaling all that. Okay. Which is, sometimes if it is not a lot of people live there, no, that's the easiest method to do it. And that depends on also the soil permeability, because you want the gas to escape. And then here is the other one here. If you see soil vapor extraction techniques, which is basically you don't want to inhale those gas, so you apply the vapors and you capture that vapors from that area, and that's for the vapor extraction. So that vapor is what you treat. That way you don't have to let the contaminated system leave the area. Um, there is any but this is actually ex situ because you are drawing, no, not ex situ, because you are not drawing water, you are drawing just the air out of it. But then there are other in situ techniques, like most importantly, the biodegradation techniques, which is what we are going to cover here, in situ techniques, where instead of taking all the polluted water, and pumping is expensive. Pumping is not just expensive because you have to spend a lot of energy, it is also inefficient, because when you pump the groundwater, no matter how efficient your pumps are, it may not draw all the contaminated water, because there are pores that will hold on to that water for a long time. So pump and treat method, sometimes for that to be effective, it has to run for 100 years. 100 years of running a pump is very expensive. Okay, so that's why pump and treat method was not being anymore used, or not used unless it's like really required, or it is always used with in addition to something else. Whereas biodegradations or bioremediations, you don't need to really pump anything. You just have to let the microorganism degrade it naturally. But now question is, why they don't do it by itself? What you need to do extra? Well, microorganisms there, they don't have any incentive to degrade organic pollutants unless you give them the stuff they need. So to increase the efficiency, you have to sometimes apply oxygens or add nutrients, all that factors, so that it becomes more efficient, or effective. So biodegradation is a very popular techniques now. Again, it's a slow process, but it can be efficient in long term, where you don't have a very you don't have to spend a lot of money on it. And then also you have phytoremediation, which is basically wherever the roots are, that roots itself has a lot of microorganisms, and also plants can uptake a lot of the contaminant. So this is mostly for subsurface, not groundwater. This is for mostly biodegradation for, can be any place actually, groundwater and subsurface. Okay. So these are the different in-situ techniques as I described before. Now, the one of the techniques is, let's say, oxidations, where you inject some kind of reactants into the aquifer materials, and those oxidants will destroy the organic pollutant. So this oxidant could be ozone, it could be, but ozone is not used all the time because ozone is so reactive. The moment you inject it, it reacts to the soil itself before it even reach there. So you have to add something which is not so reactive to the soil, but it stays long enough to react with the actual pollutant. So the oxidants that you are looking for is mostly has to be dissolved in water, and it will be easy to distribute. And also it should not be so reactive that it start reacting with the soil, so that it stays in water and keep the reactivity for a long time. So these are the different techniques that you will learn how in the CE164. So these are the design considerations you have to think of. Um, how long, what's the time for decay, what kind of oxidants you should use, how efficient it is to deliver. Because as I said, very reactive oxidants will not be easy to deliver, because the moment you deliver at that near the near the soil, that soil will be all taken up by that, or the soil will take up all that oxidant. So there will be nothing remaining for the actual pollutants. And all the other conditions you have to think of. Again, we're not going details. Again, that's the thing I said. Instead of the chemical oxidation, you'll inject those pollutants, it will find the pollutants and they will destroy that. Some of the example compounds that usually removed by these oxidants is PCE, TCE, beryllium chlorides, they're basically and petroleum carbons. And type of oxidants can be used is this. And most popular is permanganate. Again, the reason is it's water soluble and is also not so reactive that it will destroy, it will be taken up by soil. Persulfate is more reactive as KMNO4, so there are places where this can be used. Ozone is the most reactive one, and it's a gas, so that means you don't have to worry about any other side effect. But it's very so reactive that it can you have to ensure that you are actually hitting the pollutant zone, not any other places. So again, these are the decisions you have to think of. We're not going details about it, but I'm saying that these are things you'll learn in the other classes. The other cheaper method is a permeable reactive barrier, which is basically, think of, you have your garden is polluted. If your subsurface or the groundwater is very shallow and it's being polluted, all you have to do is dig the hole so that you create this big barrier and put all the adsorbent material here. So think of activated carbon, think of whatever you think that can remove pollutants by adsorption or reaction or whatever the reason. So this is what you see. They dig the entire hole here, create a wall, and then fill with these reactive materials. So as the groundwater move through it, it just have to, it will remove the pollutants. The advantage of this method is you don't have to worry about finding where the pollutants are. Pollutants are coming to you, not you are not looking for those zones, because groundwater will pass through this area. The disadvantage is that it only works for the shallow groundwater, because you can dig a hole for like 100 feet. It's so expensive. And also you have to deal with the reactive material cost. So again, these are all different things. You have to think of cost benefit analysis before you decide which one to be removed, which one will be easier. These are all things you'll learn in the C164. Another one is electrokinetic. Electrokinetic is basically um, is only applied for contaminant which are charged. As you see, electrons, it's all based on the flow of electrons. All it means is you apply voltage, you put this two big metal rod inside the soil, this metal rod, apply the voltage, positive or negative. So all the positive ions will, so let's say copper, that will attract it towards the cathode, negatively charged ion. All the negative ions will be attracted towards anode or positively charged ion, positively charged plate. So what you are doing here is it makes the pollutant move. You don't have to worry about if this is you can assess that pollutant or not. Here you are applying this voltage or creating these gradients so that pollutants can move. You don't have to worry about water at all. Why it is efficient? So think of all the pump and treat, everything I just described here, advanced oxidation, everything that we talk about. You are keep putting the contaminants, or we are putting all the reactive materials near the location which is polluted. A lot of time the clay will hold those things. So it's very inefficient for water to move out of the system. So you cannot really treat those locations. Whereas here, you don't really care about water because water doesn't have to move. All you care is that ions or the pollutant has to move out of that water. So that's why this is very efficient when your soil is soil has low K, low hydraulic conductivity. All the other system, you need the assess. Here you don't need the assess because you don't really rely on the water movement. You rely on the pollutant movement itself. You just drag the pollutant out by applying charge. So this is effective for heavy metals. This works with low permeable soil, so that there is no no short circuit. Means you don't want water to escape. So you want the water to stay, not just the pollutant to move. So again, these are the concept techniques. You don't have to remember any of these things, just because it's an open book class. Just know the conceptually what those means. All right, so we cover everything related to in situ, ex situ method. So let's see if we have um, the understanding. So I'm going to put a generic question here. So your question is, a groundwater aquifer is heavily polluted with chromium. Chromium, let's say Cr 3 plus or 6 plus. Which of the following treatment technology is effective if the permeability of groundwater is high? Groundwater aquifer. So let's start thinking. Electrokinetic works only if as just described, need permeability. Permeable reactive barrier, in situ oxidations. So for this one to work, you need to have oxidations. Okay, you have to oxidize. The chemical can be removed by oxidations. This you just learn it, whatever the way. Permeable reactive barrier is basically things has to pass through a barrier. Okay, I'm going to end the poll in next 5 seconds. So decide whichever you think, then we'll discuss that.
Professor, do you have your slides number, or like I don't know if you have them. That's why I usually.
Okay, wow. I didn't realize this is not numbered.
Oh, that's fine.
Okay, so in the poll, let's share the screen result. So this is kind of distributed answers, which is expected. 28% says this one, 39% says this, 33% says this. Okay, let's start thinking of eliminations. I just told you that electrokinetic is going to be very efficient if it is low permeable, because and I just say that this is permeability is high. So that means this is not a right answer for sure. Now let's think of number B and C. So in situ oxidations, for that to happen, you got to oxidize the chemicals. So chromium 6, what if you oxidize, what will happen? It's not chromium 7 or chromium 8. That's not going to change. So it's already oxidized. You can't, even you oxidize something, it will become still chromium. It's not going to change something to different chemicals. Unlike, let's say, carbon, if you oxidize it, it becomes carbon dioxide. So it's non-toxic. So that's why in situ oxidation, because chromium is, when you oxidize, not removing chromium, it's just changing to a different form. So this is not the right answer. And again, it says permeability is high. Your permeable reactive barrier requires things to move to that barrier. So to pass through the system. So if it doesn't move through the system, it's not going to work. So that's how you can think of how to eliminate. The last one is phytoremediations. Again, we don't need to go through this process. Just know that plants can take through the roots. There are a lot of processes that can happen. They can stimulate the microorganism in the roots so that the microorganism can remove. Some types of organic pollutants like VOC, they can actually directly be uptake by the roots because it gives that flow. It's like a highway for them. Soil they cannot escape, but if you give them the root kind of create this gradient so that they can escape from to the roots and to the atmosphere. So that's one way. So these are all the different processes. We're not going to cover neither in this class nor the other classes. Now that I just quickly browse through it, just let's see brainstorming questions. Which part of the plant is more active area for phytoremediation of soil? Root, trunk, or leaves? And I have phytoremediation of soil. I will turn up, I will close the question in 15 seconds. So this is a very, okay, so 43, almost you answered. So let me end the poll. Okay, 44 answer, so share the results. Okay, so 93% says this one, 1%, 2% here, 5% here. Okay, so the answer is root. The reason is the first thing for any of this system to work is they have to be uptaken by roots or destroyed at the roots. So that's the most active area. And once that is workable, everything else come into play. Your leaves will not get by itself. It has to go through the root. So the driver is the root. The last of remediation techniques is bioremediations, and something we'll cover a lot in the next class. Just want to give you some idea of how it works. In fact, you already solved one question in last class related to these bioremediations. Bioremediation is a process by which microorganism, which is naturally present in groundwater or soil, can destroy these pollutants. So if you think of the way it works is, the advantage of bioremediation is the destructive techniques, and it makes the pollutants in something harmless constituent, like carbon dioxide. And so it's somewhere or other, it's more attractive. It's cost effective because you don't have to pump all that stuff, and it's a natural process. So it's kind of it's more effective in long term. But some bioremediations or some microorganisms, they can also create byproducts which could be toxic too. So you have to think of what kind of byproducts. Not that all microorganisms produce make it to carbon dioxide, which is ideal, but not always that's the truth. So you have to think of what they produce at the end. But the techniques is, carbon plus, if it's aerobic bacteria, so it's oxygen. You have microorganism, or just let's say bacteria. There are bacteria, fungi, all that stuff. Okay. Then you give them nutrients because they are not going to survive just on, because they need essential nutrients and all that. And then it becomes CO2. Okay. That way there is no pollutant. So this is just one pathway. There is not, this is the most idealistic pathway, but in nature, they break into multiple steps. One compound become another compound, that some other microorganism degrade that to something else, and finally it become carbon dioxide eventually. So these are efficient for mostly many types of pollutants. So these are organic pollutants. The mechanism is very different for organic versus inorganic. Inorganic means metals. Again, metals are not changed to something else. All the microorganisms do is they fix the metal into the locations somewhere so that it doesn't move to water. So they don't destroy metal. So that's the key difference. Organic, they destroy it and make it to carbon dioxide or transform it to something else. Metal, they don't transform. They just fix that contaminants at that locations. Either they change the pH of the surrounding so that metal become precipitated metals, or stick with their extracellular matrix of the biofilm. So that's how it can remove. So microorganisms, they create a structure or create a materials or extracellular EPS or extra polymeric substance. So that's what they produce to create a biofilm, and that's basically adsorbent. So somehow it can remove those metals. But it's organic, which is more interesting because they can actually use it as a food source, or they can use an enzyme to degrade them. So there are multiple ways to for this to work. So the again, you need nutrients and all types of microorganisms. So that's a little bit more complicated. But key here is this oxidation or reductions, because microorganisms can both oxidize or reduced. So you have to think of that. Anytime halogenated organic compounds, halogenate means chlorine, bromine, all that, they're already at the periodic table of 7. So the only way for them to become removed from the system is by accepting electron. So anytime you see carbon-chlorine bond, the only way to treat is by reducing, not oxidations. So if I ask you a question, there is a chlorinated solvent and you want to oxidize, which was if you want to um, oxidize that bond, which oxidant to use? That's not possible. There is no oxidant there, because this is only way possible is reduction. So you have to find a reductant, not oxidations. So that means if you want to break this carbon-chlorine bond or carbon-fluorine bond, you have to find a microorganism that give electrons or reduce the compounds, not oxidize. Everything else here is oxidations. That's why O2 is produced or CO2 is produced, because oxygen is required. Whereas here you don't have oxygen requirement. All right, so what I just explained, let's think of, if I ask a quiz question, this is how I'll ask the questions. Let's relaunch the questions. Groundwater is contaminated with chlorinated solvent. So think of chlorinated solvent means carbon-chlorine bond. You are asked to inject a reagent to degrade or transform the contaminants. Think of contaminants or removal of chlorine. So it becomes this chlorine bond becomes, and it's carbon plus chlorine. Okay, yes. Which type of reagent we will use, oxidants or reductant? So you have to think what happens to this chlorine here. Is this oxidations or reductions when chlorine becomes chlorine 2? All right, 10 more seconds. Think of chlorine. This is carbon chlorine, so this has a bond here. So this is usually chlorine is -1. Okay, so that's -1 here. Chlorine gas, 0 because there's no charge. Okay. So -1 to become 0. So you have electrons here, extra electrons. So somebody has to hold on. This is oxidation though. But carbon chlorine bond, the chlorine becomes neutrals, and then that's how it. Don't worry about it. I confuse you right now. So let me take. I become confused when I write all this. So let me explain that different way. Okay, so I'm going to end the poll. So at the results, so 57% says oxidants, which is the way I explained. I don't blame you for that. Okay. 43% says this one. So that's because I wrote that equations. Okay. Let's think of what we discussed here. Any types of halogenate aliphatic carbon compounds, chlorine can be reduced. Okay, they receive the electrons, it becomes 0. Okay, so chlorine has the chlorine has 7 electrons at the outer cell. So their goal is to just to get that 1 electrons and become reduced. So they need electrons. So the electrons that can provide is reductant. Okay, so that's why you need a reduction process. So most of the time, you need reductant to remove chlorine to chlorine 0. Okay, chlorine minus um, +7 actually is +7 because you have 7 electrons. So if you have 7 electrons, I don't know how to write this one efficiently. The chlorine, their goal is to receive that electrons, extra electrons, and become inert. So that's why that 7 outer set electrons will receive 1 electrons, then it become chlorine inert. So that's why it's a reduction process. Any kind of fluorinated compounds.
Professor,
Yes.
can you explain again how the 7 outer stone electrons contribute to a positive charge?
Yes. So the reason I get you confused is I was talking about here is that it has whatever oxidation state, it become chlorine gas. Chlorine is 0. So this one, so this is any reaction is oxidation and reduction reaction both together. Now, so you can't have just one oxidation reduction. What process is going on? So this chlorine has here. I have to check here. This has I have to break down the steps. No, I didn't really break down the way that I wrote it before. So this carbon chlorine become chlorine bond and then become chlorine Cl2. Okay, there are multiple steps that has to evolve. So this step is what you need reductant for. Okay, then other is different things. So this step is a reduction process. Okay, that chlorine to be removed from the system is a reduction process. Because if you think, let's say, you have to have a complete carbon formula because this bond doesn't exist. CCl is not a formula. So let's say CCl4 is a organic compound. This has to go to CCl3. There is a SCS CCl3, then you have Cl minus. Okay, so this reaction is a reduction reactions. That means somebody has to give electrons here. Okay, and so that electron has to receive by reductant. So the reason you guys get confused, or also I confuse you, that's my mistake, is I talk about this one. That's the second step. Okay, that's a different story. The first thing is that this organic chemical reaction, the removal of chlorine, is a reduction process. And if you do oxidation mass balance equation, you will find electron here, not the other side. Yes, you are right. Somebody says that is chlorine oxidation. Yes, this is oxidation. Okay, because this is a minus. The minus electrons become 0 because you have 2 electrons. So this is the oxidation process. This is a reduction process. So this has to happen first before even that happen the second step. All right, so let's see any other. So what you have to deal with, what kind of reagent you need to add to have bioremediation to be efficient. So this example problem we solved in the last class, I just want to explain it again. You need oxygen if it is oxidations. You need oxidant if it is oxidation process again. Most importantly, for bioremediations, you need nutrients. So nutrients means, if you think of our body or our DNA made of nitrogen, phosphorus, and carbon. So these are the basic element, and oxygen. These are the basic elements. So when you think of nutrients, you don't look at oxygen. So you got to have that carbon, nitrogen, and phosphorus, everything. You can't just have nitrogen and phosphorus. Usually this carbon comes from the contaminant itself. A lot of times you may have to provide some extra carbon to stimulate the microorganism, but you expect that this carbon is there from the highly contaminated side as a because of pollutants, which are organic. What you don't find is nitrogen and phosphorus. That's why you don't see lots of microorganisms are present naturally there, because they don't have anywhere to grow. So you got to provide nitrogen and phosphorus. Usually that um, that ratio is carbon to nitrogen to phosphorus ratio is like, if every 100 carbon you have to have 10 nitrogen, and every 10 nitrogen, roughly, I'm just saying that it could be vary from site to site of microorganism, but this is just roughly the order. Okay. So if you know this ratio is given, you will be able to know how much nutrients you have to add. Nutrient means not nitrogen and phosphorus. So usually ammonium is added as a nutrients, phosphate as added as a P source. So you inject those ammonium phosphate, NH4, PO3, or there are many different ways. Okay, so it has N source and P source. And for oxygen, you have to add air spreading or the inject air into the ground. So disadvantage of bioremediation is it takes long time. It is very sensitive because it relies on microorganisms to degrade it. It depends on all these oxygen, pH, temperature, all that factors. So it's a very controlled environment. So you got to really have those kind of in place to be efficient. You need to monitor it because sometimes if the bacteria or the microorganisms are dying, you really don't have any degradations. So that's why any places where you have an emergency need, you don't use bioremediations. Anywhere you can leave it for 5 to 10 years, you can use as a bioremediation because it's cheap or cheaper because you don't really pump. There is no active part. Again, nutrient requirement, we explain it. Here I gave another formula, 120-10-1. I just explained it, so no need to put it. I explained these questions last time, so let's solve it again. Estimate the amount and cost of nutrients in pound needed to remediate gasoline, which is the formula given C7S16. Impacted gasoline impacted soil, assuming the nutrient ratio should be CN2 is 110:1. So the volume is given 378 at volume of soil. Volume of soil, which is basically, let's say this is the volume of soil. Contaminated soil is 375 cubic yard. Initial mass of gasoline in the soil. So I say that the gasoline amount is the mass of gasoline contaminant is 158 kilogram. The porosity is 0.35. That means 35% of the soil is porous. That's where your water is or the air is. Nutrient source is this. They give you what's the nutrient source. Means it says how many phosphorus there. Okay. And ammonium nitrogen source is ammonium sulfate. Phosphorus source is sodium trisodium phosphate. And it also gives you the cost per pound. Okay, so that way you can calculate. So again, all you have to do is calculate how much amount of pollutants you have in the system. So think of how much pollutant you have in the system. 158 kilograms. So again, this CNP ratio is a molar ratio. This is not by weight, by moles. Molar ratio. Okay, this is not because you are one C is 1 mole of C. They are not equivalent weight. Okay, the carbon weight different than phosphorus, so you cannot use kilograms as a comparison. So let's think of how much moles of carbon present in 158 kilograms of gasoline. So think of gasoline molecular weight. Molecular weight of gasoline is carbon of C7S16 is carbon is 12 times 7 plus hydrogen 1 times 16. 784 times 16 is that 100? You can calculate if I made a mistake. 12 times 7 plus 16. let's say 100 gram per mole. So that means if you have 100 grams of gasoline, that is 1 mole. But you have 158 kilograms. So the amount of the gasoline moles or concentration C7S16 in moles is a total weight 158 kilogram. 1 kilogram is 1000 gram. And you know that 100 gram of gasoline is same as 1 mole of gasoline based on the molecular weight. So that would be 580 moles. So that means if you know this much moles of gasoline present, what the mole of carbon, if you see the carbon mole is in one gasoline, you have 7 carbon. So that means 1580 times number 7. Okay, this 7 come here. Whatever that number is. Carbon, then you have talk about nitrogen. How many moles? Is, you know, for 100 carbon, you have 10 nitrogen. So 1/10 of carbon is nitrogen. So that will be 580 times 7 divided by 10. And if you think of phosphorus, it will be 1/100th of it. So this will be 1580 times 7 by 100, because the ratio is 100 to 1. So you get the number in moles. Once you get the number in mole, you are going to ask, how much the cost is. Well, you know this, you are getting this one. Okay, so you got to think of how much in 1 pound of this, how much moles of phosphorus is present. So if you take one, what's the molecular weight? Molecular weight of this one. So molecular weight of this one, if you calculate, you get in some gram. Okay, so whatever molecular weight, I'm not going to calculate it. Let's say this is molecular weight of trisodium phosphate. So that gram of molecular weight has 1 mole of phosphorus. You see, this is 1 phosphorus, same thing here, 1 mole. So 1 mole of N present in 1 mole of NH4 2SO4. And you also know what is the mole of 1 mole of NH4, so weighs. Okay, so you can get the weight of NH4SO4. So let me to have some kind of, let me search it. What's the ammonium sulfate molecular weight? Sulfate. It's, just give you an example. It's 132 gram. And so 132 gram is how many pound? So 132 gram to pound is 0.29. Oh no, sorry, 132 grams should be, okay, yes, you're right, equal to 0.3 pound. So that means, you know that for 1 mole of nitrogen is equivalent to 0.3 pounds of this thing. How many moles of there of nitrogen? Whatever mole, you multiply how much weight of that ammonium phosphate, ammonium sulfate would be, you multiply, because 1 mole of N is equivalent to 0.3 pounds of sulfate, then how many, this many moles there, so that means this will be the pounds of, this is LB per mole of nitrogen, okay. And then you know that per pound is $3, so that will be $3 per pound. Then you get the entire cost. So that's how you can calculate. Again, this is just a simple understanding of now what you are going to calculate. Just example. Again, these are just a short question so that you know how to estimate for the treatment cost. Oxygen requirement, again, the same way. The next question was, my screen is frozen. You guys are not, do you see a next screen when I see right now? So
It's on
anything,
the example.
so do you see a new screen right now, or you see the old screen?
The old screen.
Okay, so anything I'm writing is not being shown here. So let me stop share and then reshare again, because I wrote the cost, whatever I was talking about, and I don't think this is reflected. So share the screen again. Okay, so this is what I was talking about, like how the cost and all that, and the answer is this $3 per pound, and then you have to know how much pound of 1 pound of tris ammonium sulfate has how many moles of nitrogen, and that's how you add 0.3 here, and then you already calculate the moles. Okay, so oxygen requirement is the same situation. You have methane. Let's see here how much oxygen require. 1 mole of methane here require 2 moles of oxygen. So if you know the gasoline amount, you know the also moles of oxygen required to degrade it. And but now question is, if you know the moles of oxygen, how much air you have to pump? Well, that depends on how much oxygen present in air. So that's why you have to think of how much percentage of air is oxygen. So 21% of oxygen is 21% of air is oxygen. So that means moles. If you think of concentration of oxygen in air, this is how you can calculate. So PV equal to nRT. So this is moles per oxygen per volume of air is P by RT. Okay. So that's how you can calculate if you know the partial pressure. And then only 21% of that is oxygen. So that's whatever that amount, you 0.21 atmosphere is oxygen. So that means this is equal to P. So if you put that P equal to here, then you should get the oxygen concentration in air in moles per meter cube of water. And if you know how many moles of the present, then you will be able to calculate how much air you have to pump. Okay. So again, volume of air that you have to pump is moles of O2 required. Thus you can get from here these equations based on how much methane you have to treat divided by moles of O2 present in air per cube meter cube, which is here. Okay, this answers. If you divide, then you get the volume in meter cube. So this is exactly what I asked here. A subsurface content 5,000 milligram per liter of benzene. The air in the subsurface is relatively stagnant. The total bulk density of the soil is 1.8 grams. So let's start calculating. So first of all, whatever we know, subsurface content 500 milligram per liter of benzene. So you know the concentration of pollutant. Concentration, so I'm going to write C6S16. Concentration is 5,000 milligram per liter. Again, you have to change to moles. Okay, so everything is molar. So that's 1,000 milligram is 1 gram. And if you see the molecular weight, C6S16 is 12 times 6 plus 16, 98 gram per mole. So that means 98 gram is 1 mole of things. So that you get in moles. And if you see the amount of oxygen required, you know that C6S6, if you, oh, I made a mistake here, S6, not 16. So that will be 78. 78 plus 6O2, it'd be CO2, 6CO2 plus, I think 6H2O. See. No, that's not true. CX, 6CO2. We have to balance it. It's not balanced. 6CO2 plus, let's see, 6 carbon is balanced. Now you have a 3 oxygen. So let's say, hold on, 3H2O. That's a 6 oxygen. So now you have extra 3 oxygen. So that means you got to have another 1 point. So that will be, that means you add 3 extra oxygen this side. So this side you have to add 3 oxygen. So that will be 3 by 2 oxygen more. So when you add that one, 3 by 2 plus 6, so that will be 7 point. So it will 1.5. So that will be 7.5. Okay, just going to make it here. That's the balance. Okay, so that means you need 7.5 mole of oxygen. So you need how much moles of this one present. So that means you know oxygen required is 7.5 times whatever here is. Okay, that's moles. So you know that in terms of moles. Now question is how much total bulk density is 1.8. So that's per liter. Okay, so that's per liter of water. But now how much water you have to treat? That's what you have to find out next. Total bulk density of the soil is 1.8 gram per centimeter cube. The degree of water saturation in the soil is 30%. The porosity is 40%. Determine the amount of oxygen needed. Estimate the amount of oxygen available in the pore water. Blah, blah, blah. Okay, so that first of all, determine the amount of oxygen needed. So think of, did I tell the size of the soil? Okay, let's think of the in 1 liter, in a 1 meter cube, because somehow it doesn't say the volume. Think of what's given. If you have 1 meter cube of soil, whatever the volume of soil, only 30% of that volume of soil is pore. That's where the water is. So 0. Porosity times volume of soil is the porosity times volume of soil is the pore space. Okay, the entire volume of soil. Then among all the pore space, only the saturation of the 40% is filled with water. So that means you have to treat only that portion. So this is the total volume of water. So this is 40%. This is 30% porosity, and this is what supposed to be given to you while the contaminated site. Once you know the volume of water, you know the moles of concentration needed per liter of water, then you can calculate the total amount of oxygen needed. Now you calculate the total amount of oxygen in moles per liter. Then it says estimate the amount of oxygen available in the pore water, assuming the solubility of water is 9 milligram per liter. So now how much oxygen is actually available in that water? You have to think of, this is the amount of oxygen needed, not amount of oxygen is actually present in the water. So think of how much water you have in the solution. So the volume of water is given already, times concentration of oxygen in water, which is the total amount of oxygen available, O2 available. And this is 9 milligram per liter. And volume of water you already calculate. So that will be the amount of oxygen available. So that you'll get milligram per liter. Again, convert that to moles per liter, then you know that the amount of oxygen needed is way, way more than what is available. That's why, in fact, you have to pump. Okay, again, these are just the mass balance calculations. So calculate that value so that you have an understanding. But again, these are just the concept. So
Professor,
everything, yes.
what did it say at the end? Like, it said volume of water times the concentration of O2, and then equals to O2. Uh, what's that word in the end?
Way too available in water.
Oh, okay.
So concentration of O2 in water times the volume of water is the amount of O2 available. And this
Oh,
is
okay.
O2 needed is the concentration times the pollutants that you need to treat. Okay. So this formula that I explained is already given here. So those are the things well. So I again just know this formula so that you know the concept. It's really not. I'm not going to ask any. Basically, I'm asking how much volume of water in soil. That's something you already know based on porosity times the volume of soil. And then now saturation is just extra term because not entire volume is filled with water. So that's why here. How much volume is air filled with air? That's the rest of the amount which is not filled with water is the, so that's why it's 1 minus S. So that's all for the questions for, I think, we have few remaining slides about how to manage landfill, all that. So it will take 5 minutes for me to explain it. So let's finish that one, even though we are kind of close to the end, 7 more minutes remaining. All right, so again, these are just concept. You don't really need to know the design or details, everything. Just know these are all exist, and you learn a lot about this in the CE154. So one thing you realize that we are treating water most of the time, and those water treatments produce waste because you are removing pollutant from water to activated carbons, or you are creating sludge if it is wastewater treatment plants, or you are also producing lots of solid waste, which is basically we didn't cover, like your trash, and so they all go to landfill. So how do you design those landfill? Because at some point you are producing so much waste that you will run out of space for landfill. In fact, in Europe, you cannot make new landfill anymore. You got to find a way to use the same one. So that's why, because of the restrictions, they are either shipping their waste to Asia or some other site, outsource. And now that is also banned in many countries, so they don't have any place to go. So that means they are now creating a new system where you can actually manage your waste by itself. In the sense, you use those waste to produce something else. So, for instance, instead of dumping all their plastic waste to, let's say, Vietnam, and many other countries, don't take one country as just because I name it. It used to send to China, but China banned it. So now what they're doing is they're actually using those plastic waste to produce something valuable product. So it creates this incentive. So most of the time, normally how we manage waste is landfill. Landfill means how it sounds. It's a land filled with waste. Okay, so you have to keep big hole, and then you dump all the waste and cover it up. So that's how normally it sounds like. That's how it has been doing. But actual design is more complicated because you have to put it such a way that no gas can escape, no pollutant can go into groundwater. So those are the two things you can think of. And now modern landfill is not about waste, it's about actual resource. Because what they realize is they are taking all this waste and they are producing methane. So instead of having this greenhouse gas emitted to atmosphere, they are now saying, why not we capture that methane and produce electricity? That way we can sell off that energy. So that's what you learned in the last class or last week of the class. But I'll just give you a concept based on those. Again, my screen frozen. I am going to a new slide, but I don't see that is going on. I don't know what's going on here. I'm going to stop share and again restart. I think the computer is frozen or something. Okay. So again, the main function of the landfill is to limit exposure of waste to environment, to limit the leachate so that you don't pollute groundwater, to capture the gas for energy productions, and also to degrade some of the pollutants if applicable. So this is how the landfill look like. If you see, they are well-engineered landfill. You have different system. You have the very bottom is you have a layer of system so that it prevents all the um, pollutants or the leachate to not inject into groundwater. And so that's why, first of all, when you design this landfill, you should put the landfill in a place which the soil is extremely um, impervious. That means clay soil. Any site which is so much full of clay is a great size for landfill, because you already learned in the class that clay do not allow water to move through it. So that means there is a low risk of groundwater pollutions. But even though there's a clay site, then also you have to think of, is this an earthquake area? Means you don't want the earth to come out again. So that's why a lot of landfill has to be in the zone where you don't have exposure in accidentally in future earthquake time. And then also you have to think of, is this a place where the groundwater is very near to the landfill? If it is, then you don't want to. Also, you want to put a landfill far away from the surface water, because if there is a spill, there is a leachate is not going to go to that pollution. So after you take care of all those locations, now you have to dig the hole and you have to create different layer. So you see up to here, all these layer you see over here is all about preventing that leachate to get into ground. So you see there is a geo under drain mat, then there is engineered clay, means basically it's a so compact clay that water doesn't move. Then you have a plastic high density HDPE membrane, so that plastic will prevent any water to go through it. That will also protect that engineered layer. Then you have a kind of porous membrane, because you want any kind of gas or anything that goes there to extract it, secondary collection geonate. Then you have a low permeable soil. So again, that low permeability to have that barrier between them. Then manufacture clay. So you can keep seeing there are clay, membrane, there are so many different stuff. So you put all the different layer before you start adding any garbage. That way you have the system to prevent any kind of leak to groundwater. And then finally, at this point, you have this porous membrane, perforated pipe, and porous membrane to collect any kind of leachate coming out of this waste above it. So now you are going to start adding all this dumped um, um, plastic trash, everything. And the way it works is you dump all the plastic in a layer, and then you fill it. At the end of it, you fill it with a soil. That way you can compact them with using a bulldozer or any kind of. So that's why you see there are different layer, and in between there is a soil or some kind of intermediate layer, because you don't want them to expose to atmosphere rain all the time. So to prevent that, you pack them and cover it up with something kind of so that if there is a rainfall, it kind of doesn't get into landfill, it goes out of the system. So they receive all the waste, then they fill it up, and then they create this kind of layer. And then above it, you have to manage for gas. So once you complete that entire hole, and you don't have to collect any more waste, you then put this kind of membrane again, just to ensure that the gas will not escape, or there is no rainwater that will get into the system, because you don't want water to fill it up, the pores, because more water, more leachate, there's a risk of groundwater pollutions. So there are barrier, all these topsoil barrier are all about preventing rainwater getting into the system, as well as capturing the gas that comes out of the system. So there are many types of landfill. This is what I describe here is just the municipal waste. There are industrial landfill. There are toxic that can receive toxic waste. There are also landfill which just receive construction debris like a cement, wood, and all that stuff. So those have different design requirement. So all those things can vary, but this is the concept that I just described. So we are now above the time. So just because we have 5 more minutes to, I'll just go ahead and record it. If you have to leave, just leave. That way we just put those on the recording. So municipal solid waste management. No, so this is different. The type of waste it produce, it capture is the basically what the waste we produce, the household waste. That means non-hazardous. And again, as I already explained this one, its location has to be away from the fault, on the earthquake faults or wetland, surface water, or any kind of groundwater source. Got to have composite liners, that's to prevent the leakage. You got to have a leachate collection system because most of this municipal waste are actually food waste. So those will decompose, it will produce this slime or the water, and that water has to be captured because you don't want to let it fill. Because if you fill the entire landfill, those are toxic to microorganisms. Then that means they will not degrade anymore, those compounds. So that's why you have to collect those leachate and treat them. And then you also have to compact them to minimize the space. Also, that's why you have to keep adding some kind of cover in between so that you don't have rainwater going in. And then you have to do monitoring of groundwater to ensure they are not being polluting other systems. And then at the end, when you finish the entire landfill, you can close it and make sure that you have a very, very compacted topsoil and gas collection system so that you can continue to produce energy over times. So that's why you see this energy. And again, the links are given. If you want to know more about it, just go to the link. So I already explained the system, the location requirement, and what's the composite liner. So everything, if you go close to here, it shows exactly what are the other things are. So without telling you anything, now that I told you all those different concepts of here, let's think of if you can able to identify those. So this is not a quiz just to, you don't have to choose A, B, C, D. Let's look for the layers that does that. So can anybody tell me the first one, to limit waste exposure to environment, which are the two layers you need? It's hard to say, just let me write it here. 1, 2, 3, 4 here, 5 here, 6, 7, 8, 7, 8. It's based on the what type of layer you have. 10, 11 is this. If you can read, that's why I'm writing it here. This is 13, 14. Okay, so can you identify the numbers to limit the waste exposure to environment? Which are the two layers? Which does that?
I would guess 6 and 7, maybe.
All right, let's think of where the environment is. Either top or bottom. Bottom is groundwater, top is air, right? Atmosphere. So the bottom one, which one is the, which one is protecting? So
14.
So yes, 14, 13, because there is also a layer and also 12. Okay, that's the bottom one. What about top?
2, 3, 4.
So usually these are actually not the protection. This is mostly about the plant to survive, all that. The protection is the clay here. So 5,
6.
6. Okay. These are growth membrane. This is for growth. This is protections. This is protection. And this is leachate collections. Because you see these are gravel, big gravel. So again, I didn't tell you to read everything. So that's why it's just you are guessing all the things. Okay, to limit leachate leaking, which one is the one? I just explained it. So which one you write? Leachate leaking is the bottom layer.
11.
So that will be, that's the actual leachate collections. So that will be 11. Anything greater than 11. Okay, because 11, 12, 13, 12, 13 also is not going to leak into ground. Which one to capture gas? Think of where it is being produced, where the gas is produced. gas is produced here, okay, in the west. So think of where the gas will go.
Would it be 7?
Yes, because you have clay over here, so gas cannot permeate through that one. So that means this 7. To degrade pollutant, if applicable, which layer? Which one degrade pollutants? So think of where the pollutants would be. Let's say water.
8?
Yes, so that's 8. Here the source of pollutant. So you can degrade by biodegradation there. And any leachate come here, you can also degrade here. But this is external degradations, ex situ. This is in situ. All right, so you guys now know everything about landfill in terms of its design. So how long it takes for biodegradation to occur inside the system is based on this degradation rate. It's a first order decay. So a lot of time, all they do is they calculate those values based on these functions. So this is the equations that people use. Again, you don't have to think of all that. All you have to think is the temperature dependency. Because if you see based on these reactions, the reaction is more efficient if the degradations occur, the temperature is high. So this T is the denominator. So this means if you increase the temperature, this entire term becomes smaller, and this is also this is negative. That's why the term is the denominator. If the denominator becomes smaller, the degradation rate is higher. So if the temperature increases, okay, rate increases, that means degradation is more efficient. So if I ask the question, determine the leachate production in summer versus winter, you know that in summertime, the degradation is more efficient. So what they do in the cold climate when they design landfill is that they have to actually apply heat. Okay, so they have to actually have a heat pump to add the hot air into the landfill for this thing to operate efficiently. Sometimes they sprinkle also water to as the hot water just to have the temperature high. So, oh, I already asked the question. So let's, for sake of it, let's relaunch the poll. Biogas production landfill is greater in which season? Okay, again, I just end the poll here just because we discuss it. It's in summer. And again, I just want to reiterate how long it things to pass through the system is based on the Darcy's law. We already learned it, so I'm not going to discuss again. So this term is distance. This is the depth divided by velocity of water. That's Darcy's velocity by porosity, and this Darcy's velocity is k times I. I is usually 1 for a vertical transport, so that will be kn divided by dn by k. So if you calculate this one, you should be able to get that number. So if the clear liner has a depth of 1 feet, so d is 1 feet, and the porosity is 0.5, how many years it will take for the leachate to migrate across the clear air? And the k is given this one. So again, the time would be distance 1 feet divided by this k is 10 to the minus 10 feet per second. I is 1 because vertical down gradient, so that's porosity is 0.5. Again, if you want to convert to year, so you just have to say how many seconds per year. So let's say 60. So this is 60 seconds per 1 hour and 24 or 1 minute. So then 60 minutes per hour, then 24 days. So this is second per day. Then you have 365 days. per 1 year. Then you get the time in year. You will see that is a pretty long number.
Professor, so the I is pretty much the depth of
No,
the,
this is hydraulic gradients.
okay.
Gradient. That's dH over dl. So the head drop per length here, because vertically moving, the vertical depth it migrate is actually the head drop. So it's a dH and dl are equal. So that's why it's usually equal to 1 in a vertical transport. Again, this is just takes many years. You'll get that it's like 365 or 300 or 400 years, so which is pretty much the time all the contaminant will degrade anyway. So you don't have to worry about that leachate transport. I'm not going to cover this one. I just want to say that these are something where landfill can be used to capture that methane gas. So they are anaerobic reactor, they are aerobic bioreactors. So basically just read those texts so that you'll know. And we'll cover those in the last class in terms of how you can manage the waste as a source of energy. And landfill is going to be a source of energy in a way. All right, so next class is air pollutions next week. This is all end of the solid waste management. Thanks for staying late today. And you have a great Thanksgiving weekend. And I hope to see you on Monday. Again, reminder that I will post the example questions on the homeworks today, end of today. Watch those videos if you have questions on that. But most importantly, if you have any question or difficulty, just ask questions on Campusware, because those questions will help me also posting more videos, or at least set up new example question for Tia to discuss on Monday and Tuesday, so that you have enough time to answer those questions. Let me see any questions on the chat window. What day will be the final? So that's already decided, but again, this will be also a 24-hour window, so you don't have to worry about. So that time is already there in the syllabus from the day one. That's decided by the university. The question about 902, so I don't know those. Okay, all right, so I think that's all. See you all next week, and again, enjoy your Thanksgiving. Stay safe, and I'll stop the recording now. Stop share.